Thank you all for coming. I really appreciate the turnout. We're with Sony, and we're going to talk about breaking the bandwidth barrier using soft state and ELB properties. Yes, that's what I want to hear. ELB, yes, yeah. Let's do it. OK, so first I want to show this.
Now starting at $299.
That's right, guys. For the low price of $299, you can have a PlayStation 4. All right. So, who's talking?
That's me. I'm Alex. I work for Sony Interactive Entertainment.
And I'm Dustin, as you can read on the slide. So we're here to talk about a couple of things. The agenda here is basically first talk about PSN overall and what kind of services that we work on and what offerings we support. We want to talk about the classic stateless architecture that everyone's probably really familiar with and probably doing at their jobs. We want to talk about soft state, what that is, how it applies in a complex system. And like I said, how we applied it into one of our major use cases and how it really helped our performance. So more about PSN. The PlayStation 4 has been really successful. It's been big and growing. You can imagine that every PS4 sold is more calls to our services. So we have to scale out accordingly to the growth. So we have over 65 million monthly active users. We have hundreds of millions of users just on all different platforms other than PS4. We have more than 47 million PS4s. I think we actually sold even more over Black Friday. And we have a lot of offerings. So some of those offerings that we support, or at least our team supports as well, and some other teams, is the PlayStation Network, everyone's somewhat familiar with. And in there's PlayStation Store, which is the console store, the web store, mobile store. All these are powered by our services. We have PlayStation Video. That's where we have streaming movies, TV shows to your console, onto your laptop. We have PlayStation View, a really cool service that is really disrupting things. It's streaming like live television over the web. We have PlayStation Music. We have a partnership with Spotify. We offer game-related playlists and all that. So it's pretty cool. And a really cool service, PlayStation Now. It's really innovative, streaming games to to your console, to your television, to your laptop. It's really awesome. So a little bit more about our services. We have our social presence. And this is one of the features we want to really focus on, and this is a friend search. And if you can imagine with the numbers I mentioned, about 65 million active users, you can imagine what that social graph looks like and how this particular feature kind of feeds into itself. Every friend you make makes the social graph more complex, and we have to be able to manage that complexity. And we also have to manage the search in that. We also have our hybrid of, I guess, Facebook and Twitter. We have our own social network, which tracks your activities. We share when you play a game, when you make friends, when you earn trophies. That's part of what we do and what we show. We have this thing called communities, which is, I guess, user-created forums. So people who share common interests in games can create their own communities and then just share in the gaming experience. So there's a lot of different offerings in the social realm that we provide. And you can imagine at scale, it does add quite a bit of complexity. And in video, we stream, similar to Amazon Video, we stream movies, TV shows to the player's console. We also do things like PSV, like I mentioned, which is really cool. It really competes with companies like Comcast, AT&T, Uverse, and all that stuff. And it's really, really, really cool. Okay? And in commerce, here's PlayStation VR. Just be able to buy games digitally on different platforms. It's really cool. But all of these services, there's something really important that we have to talk about about these services is that they have to be fast. Gamers especially are expecting low latency. Any kind of latency in games, they would expect no less from the rest of the platform. So it has to be fast no matter what. So let's go a little bit more into the classic stateless design. It is the go-to design. Everyone does it. Stateless design is your application tier is basically you can tear it down, has no state. A user can land on any box, it doesn't matter. And then your persistence is in your database. So basically there's a clear distinction between your application and your database. So the database holds state, your application tier holds no state at all. And pure stateless systems are, I guess, extremely rare in some cases, like a web calculator is a good example. There's always some concept of state, and we'll go a little bit more about what that looks like in terms of search. And honestly, I think this stateless practice is taken to a far extreme as a religion. That no matter what the use case is, we'll just do stateless. And I think that as you go to different scale, you will need to have different architectural patterns to solve those use cases. And I think following this pattern is useful, but there are times where you may want to kind of deviate a little bit or just kind of augment it a little bit. So here are the pros of the stateless design. Obviously, it's easy to scale horizontally. If you have, you're running out of resources on a particular box, you can just add boxes infinitely. You end up with thousands of servers, and you're able to serve the customer. Easy to program. You don't have to care about state. You just throw the state back to the database. That's all you need to do. That's how you code it. Works on multi-regional deployments. You don't have to think about where your data is necessarily or where your application lives. It just has to know where the data is, and then that's all you need to do. And that's only true if your underlying tech works. Let's say your database needs to be multi-regional. And it's a really good step to serverless architecture. Stateless, with serverless, it goes hand in hand. So some of the cons are you're really relying on somebody else's code to manage your state. You're relying on distributed databases like Cassandra or Couchbase or something like that to be able to persist your user's data and just hope your application can scale with it and be able to perform with it. But there are actually a lot of complex use cases where there's going to require a lot of network communications. You can imagine, as we're dealing with large social graphs, there could be a lot of calls back and forth to the database, to other microservices, and the network traffic is quite large. And eventually, what you run into is that actually becomes your new bottleneck. No longer is it the amount of requests that you can serve from each box. Now it's the amount of throughput you can get out of your databases or your caches, and then it becomes, at a point, even impractical to do or very costly to do. So, and then if you think about all the boxes that you have, they have different dimensions. They have CPU, memory, network, and disk, and all these things. And you're going to hit a bottleneck for one of them, but there's resources left on those instances that are not used. Why not use them? You're paying for it. Why not take advantage of it when you can? So, a lot of systems look like this, right? You have a client calling a microservice calls another microservice, and you can't track the call pattern, and then magically, something works in the back. It's your state. It's back in your database. It's managing everything. And all those calls through don't really know about the path it took to get there, and that path can be very long. And that's the hope that a lot of stateless system is that, okay, well, my data tier, my caching tier will be the one that will be managing everything. So what are some of the cool alternatives to this? So obviously there's Lambda architecture. You probably hear about here in AWS, the Lambda feature. Or we can just talk about soft state. And what is soft state? So soft state is basically accepting the fact that state exists and use it to your advantage. Okay? So more about soft state. In computer science, soft state is the state where it's a state that's useful for efficiency, but it's not central. You can recreate it or regenerate it if needed. There's a picture of my car here if you've ever seen it. It's really nice. So a little bit more about this. This car is actually very appropriate for soft state. Alex?
Yeah, because it's a pretty interesting car. It has an electric engine inside, but it's not there to save you money, right? It's not gonna do it. I think it can make like 15 miles on its batteries. It's there just to make you drive faster, accelerate faster, right? It accumulates energy when you brake, and then when you need a burst of speed, right, of acceleration, it just gives it back to electric engines. And then I think the standard engine can do like 600 horsepower. Together with electric, it goes up to like 800 horsepower. So if you think about it, it's very interesting. It's kind of similar application, right? You have something that is inside just to increase the speed, literally, increase the acceleration.
Yeah, so that's essentially what we want to do. Why don't we make systems that are like this Porsche as opposed to the tried and true, I don't know, Honda Accord, which I have as well, for real. It's actually a good car, but okay. So some highlights. Whoops, okay, you saw too much. I revealed it all. Okay, so some of the highlights is simple state that's kept in memory for performance. Like Alex said about the car, there's something that's there that is just there to make things perform better. You don't have to have the car still drives, your system still works, but it helps, and especially in high performance systems. It's harder to program, but you can save a lot of money. And we're all smart, we like to program hard things, and our bosses like to save money, so it's a natural fit. And some systems are not feasible without it. I think when we go into what our use case is, it was very hard to do it in a stateless way. So why bother? These are latency numbers everyone should know. There's a link here. I think a lot of people have probably seen this link. And basically what it reflects is the order of magnitude difference between cache hits, branch mispredicts of a CPU, and when you hit disk and all that. There's a lot of stuff. So in English, let's say an L1 cache reference on the CPU takes 1 second. So that's as close you get to the processing. Then you have branch mispredict. From the CPU optimization, if you mispredict, it's going to cost you an order of 3 seconds. And as you keep on going further away from the processing, the core, it gets super slow. And then you can imagine as you go further and further to eventually even network, you're going from 1 second to 3 minutes. So from your request, you're going such an order of magnitude further away from your high-performing system. And it just keeps on getting worse. If you think about it, as you're reading from memory, if you're reading from your disk, if you're reading from anything outside in the same data center, when you hit the disk, and if you just go even multi-region and hitting other regions, that's like 4.7 years. I mean, you just don't want to wait that long, right? Yeah, still waiting for Half-Life 3. Okay, anyways. All right, so this very smart man, what is this, Isaac Newton, has said, and I quote him, is even serverless architecture is subject to the laws of physics. So you can quote me, quoting him, quoting somebody else on that. So, but there's still a server somewhere. There's still something that is serving the end user. There's something there. So serverless, there's some server. Okay. So a little bit more about the Friend Finder feature. Is Alex going to talk about it?
All right, so now let's talk about how to apply all this theory. Yeah, people usually say theories are good, but practice actually is much more important because something that works on a paper doesn't work in real life. So Friends Finder, it's a feature that allows PlayStation users to find other users on a platform. It's also a little bit more than that, but like in a nutshell, it's very simple. So let's look at our social graph, right? There are like big social graphs in the world. Facebook is a good example, Twitter another good example, and then there are others, but ours is pretty big as well. Hundreds of millions of users, and it's growing actively. So it's growing actively because we keep adding new interesting features to help people to create new connections, discover new players to play with, and also there are like rich networking features. The graph itself, it's not just person to person per se. We have PlayStation Store, right? So we know what people are buying, we know what people are playing, we know who people are playing with. So the total graph can be really, really big in terms of number of connections between them. And then those graphs are huge, and they're growing fast as well. And then at some point of time, I think 2 to 3 years ago, we didn't have search. So users couldn't find each other on the platforms. The only way to create a connection was to just literally type like online ID or sign on email ID in the field, and you had to know it somehow. And then we had this internal hackathon when one of the teams implemented a very simple implementation. They show it, they shown it, they said like, look how cool it is. And leadership said, yeah, let's do it. So we decided to do a new feature. The idea was users should be able to find each other on the platform, like simple. There was some interesting requirements, privacy settings, right? We should respect them. If Dustin doesn't want to be searchable, and for some reason he doesn't, so you will not be able to find him, but you will be able to find me if you just type my name. So also we want to be able to recommend new users to new like friends, new connections. LinkedIn does it, Facebook does it. Like it's usually called you may know feature. It's like, hey, like there are people who look like you, or you might know them, or maybe the way you play is similar, maybe you want to create a connection, right, this feature. And there's another very interesting one, actually. The way we wanted to display results of the search, right, it should follow the following order. Direct friends first on the top, friend of friends on the bottom. So now, this one is interesting. Think about it. Let's say I have 2,000 friends. Each of them, right, has another 2,000 friends. So the total number of possible search hits is 4 million, right? One multiplied by another. Smaller websites, they don't have even 4 million number of web pages or documents. And that can happen if you just go and type search, right? It's possibility, technically, to end up with a power user, because a lot of power users as a friends. And we had to somehow figure out how to do it. And then everyone else on the bottom, all right? Friends, friends of friends, everyone. And then, of course, right, as Dustin said, bosses love like to make it fast and not really expensive. So the idea was to do it really, really fast with a really small team of really talented engineers. So in other words, that's our problem right there. So let's say that's me on the left. So there are direct friends of me, and then my second tier. And then when I type something, I want to see the first one of those SAC boys first, then like second tier, and then everyone else. How hard can it be, right? Pretty easy problem to solve. So we've figured out, so for everyone, for a platform-wide search, we can use Solr. Do you guys know what Solr is? Yeah, all right. So for people who, Solr. For people who don't, so Solr, it's open source search engine based on another open source library called Lucene, very, very popular. There's another one called Elasticsearch. We used Solr before, and then we just decided to go with Solr for this thing. And then, naturally, if we're going to use Solr to index everyone, maybe we can use Solr to index relations between users. And then if we index it somehow, we can solve a bunch of use cases. For example, we can just sort by distance, right? If we figure out how to index it, then let's say distance 1 means your direct friend, distance 2 means friend of friend, and so on. We can also sort by some other fields, possibly, right? For example, if I played with someone, often we can have some increment field somewhere, maybe, and then we can just do another sort. Could be a really cool feature. And then you may know, at the end of the day, is literally another search, and that's actually correct search, right? One day, one of the social networks, a very famous one, suggested me in the list of suggestions, there was like same person twice, and then we didn't want to end up in the same situation, right? And then with search, it should be avoided because results will be filtered. So there's a big but. Data has low and high cardinality properties. Some things are timestamps. Some things are maybe some types. It's not really easy to actually index it properly. It is possible, don't get me wrong. It's just not easy. Another thing, the question was, how do we index relations between users at all? Do we put everything in, so do we create a document, search document per user, and then put IDs of all direct friends and friend of friends, that could be a really big document at the end. And then last time I attended Lucent conference, there was a question to one of the creators, like someone asked, like, what if we do a document with 10 million fields and properties? And then the answer was like, laugh. It's not really a good idea. And it's actually not even obvious how to do this indexing. Maybe we can index relations, but then what we're going to be doing, it's a joins inside. This year, Solar, I think it was this year, they announced graph traversal, which is cool, but it's not really fast if you think about it. They can traverse, I think, almost like 1 million documents per second to figure out connections. And then it sounds like a lot, but if you have a huge graph, you'll need a lot of machine, and then you'll need to figure out how to fit all the stuff in memory, because it's performed when it's in memory. So it is tricky, not obvious how to do it. And also Solr wasn't designed for to solve such a problem. It was designed to index whole internet, right? DuckDuckGo does it. I think they use Solr. You can index your website, that's just fine, right? Solr has concept of cores. You have multiple separate indices, and then size and size index should be sane, right? Number of documents. It can go to billions, but after it hits some number, it's hard to reindex. It's just really hard problem to solve. So we ended up with some options. So one of the options, and then you're probably wondering, like, why Solr? Graph database. There are so many nice ones. Neo4j, one of them. TitanDB, another one. What else is there? OrientDB, right. Thank you, Dustin. Teamwork. Yeah. So there are a couple of databases. We looked at them. And so the problem was some of them didn't scale well in our circumstances. Some of them were hard to maintain. Some of them master-slave. Master-slave doesn't... it kind of, running master-slave on a big scale feels dangerous, right? But it's still possible. So we looked at them, and we decided not to use them. It feels like it's a graph problem, but it is not. For example, there will be another talk tomorrow about Go and multi-regional. And then we actually use Neo4j to do some interesting stuff. And then we used Neo4j core language to give us an idea how to get to multi-regional faster, right? That was a graph problem, actually. This one, not really graph problem. It's a search problem. And then another natural idea, okay, we have those NoSQL databases and stateless pattern. Let's just dump everything in one big NoSQL scalable black magic driven database and then see what happens. And then processing layer can be just a stateless thing that's sitting in front of it, getting request, querying the database, the big database, just doing something and just returning back. And that was an idea. So we came up with a schema. So if you're wondering, that's Cassandra's schema, right? But can be just slightly modified, and it could be fit in like any NoSQL database. So the idea was we have account ID, that's me, let's say. Then we have friend 1, friend 2, and then so on, my friends. And then there's some JSON that represents friends. So it's Dustin. All right, here's his gamer name. Gamer 0.
You can try it. Yeah.
How did you get 0?
I don't know. I have no idea.
Yeah, OK. So that's the schema. And then, because we all know NoSQL scales, right? Linear scalability always works. We thought, nice, now it's going to work. The only problem was, how do we do queries? NoSQL database called NoSQL for a reason, right? They don't support SQL-like queries. And then, even though Cassandra has a query language called SQL, and Couchbase as well has query language called Nickel. It's not a real query language, actually. So we thought, what does client want? Client wants to be able to do search, sort, filter. Right? Pretty simple. What can we do? So we can use some secondary indexes. For example, Cassandra has a built-in support for it, and they just recently improved it drastically because previous version wasn't good enough. So we couldn't use it. Couchbase also has something inside indexing as well, but it's all the implementation. They do they try to mock the Solr search pattern, the search across, right? The search across all the users, for example, search across all the rows. So you can kind of do a SQL query. It's slightly slower, but you can do it. And that doesn't fit our use case, honestly, because we're not searching across. We're searching inside. So another option was, let's just fetch everything in memory, stateless. Hit the database, say, OK, for me, give me all my friends, friend of friends. Could be a lot, and just fit it in one huge array or some smart data structure, do sort, filter, and then discard the state immediately, return back to user. Or there's another idea. You know how developers constantly complaining that they go to school, they spend like 4, 5, maybe 6 years learning computer science, all those cool algorithms, and then they get hired, and they just do some move buttons, on the web page. All right. I've been through it. Yes. Yeah, pixel optimizations is not fun. So we thought, OK, maybe we can apply computer science, and then maybe we can just index it, right? We have all this JSON. Maybe we just index stuff for one single user. And writing an indexer sounds like a lot of fun. You need to apply some computer science, know some data structures, there's some cool optimizations you can do. But unfortunately for us and for the team, right, someone already had all the fun. And someone created Lucene, right? So Solr is powered by this library, open source, pretty fast. Though some people on the internet even say they can implement Twitter easily with Lucene in 5 hours. Yeah, maybe. I don't know. But it's open source, it's a Java library, and then you can just plug it in and then index everything. Solr literally is a replication layer on top of it with some really cool plugins, but the core is still Lucene. They go together hand in hand. So we said, OK, let's do what we thought we can do. Let's take our schema and then just plug in Lucene right in there. So you can say I removed some stuff. I have this friend, and then let's say there are multiple friends in between. And there's this Lucene index and some version. If you're wondering what's inside version, just some metadata. The reason is we need to know what version of Lucene was used to create the index, so we can read it, right? We also need to know what fields were indexed inside. For example, did we index last name and first name and email, or did we index anything else? And then we also wanted to be able to move between different schemas easily, right? So this whole thing went to the version, so just some metadata. So now, with this new update, with this new idea, we can search on anything inside the raw. So technically it gives us a search capability, right? We have a personalized index for every single person. And indices are also pretty compact. If you think about it, they depends on number of fields, depends on the stuff you're indexing. Could be 1 to 10%. I think for documents it could be 20%. Not our case. It's much smaller. And then because it's small, it's pretty fast to put it from this database. Right? It could be like maybe 1 kilobyte, or maybe 50 kilobytes, 100 kilobytes. It depends. It's much smaller than an actual data set. But we'll still need to pull all this data all the time from indexes, from the database. Can't we do better? Maybe we don't need to over-optimize. But there's another problem. Because we have an indexer somewhere, right? I didn't talk about indexer. I talked only about read paths. We have an indexer somewhere. It could be multiple indexers somewhere. So if there are multiple indexers, there could be race condition between them, right? You send one friend request to Dustin, another friend request to me. We both accept it in a similar time. If it ends up in a different indexers, you can end up with an actually messed up index. So what can happen, the first index will be with Dustin and everyone else. Second index will be with me. Yeah, you might say there are ways to deal with this problem. There's like optimistic lock-in. But then you say this very interesting word lock-in, which kind of hard in the distributed systems. But maybe we can do better. Like it's figured out. So what could we do? We can do the, so you might wonder why you like looking at this orange fridge. Anyone know? Anyone has idea why? Right, so this fridge, so sometimes what happens a lot to me, sometimes my wife asks me, hey Alex, what did you do today? And I just put some cache in front of some other service, and what is cache? And now here's a problem. She's a pharmacist. I cannot just explain it easily to her. I have to come up with all these weird explanations. And then for a cache problem, I come up with a fridge explanation. So the idea is, if you want to have a fried egg, you don't go to Costco to get like 2 or 3 eggs. Like no one does it. Does anyone? All right, good. All right. Yes. So what you usually do, you go there, you buy a pack of eggs, you put it in your fridge, right? And then it also works like LRU cache, right? If you keep the stuff for too long, it gets spoiled, so you just throw it away. And then also the Costco or Safeway or any grocery store, right? They have some. It's not like farm deliver stuff right into the store. It doesn't work that way, right? There are some aggregators somewhere, some distribution centers, like multiple layers of caching, and then you have your personal cache right in your house. So applying this fridge, right? You want to keep the thing to your microservice, right, as close as possible. You don't want to go to a neighbor's fridge across the road. It's not nice. Don't do it. So you want to do it. And then in our world, there's some multiple things you can use. You can use memcached or Redis. On AWS, you can do Elastic Cache, which is memcached or Redis. You can have Aerospike, Couchbase. There are like a bunch of different alternatives. And they're more like a Costco in this example, actually, because you still will pay network penalty to get to there. And then you might say it's not as bad. I think from a earlier slide, we said that round trip in the same data center takes a couple days. Anyone can wait a couple days to get a fried egg, right? 5 days. It's OK. I read human can survive like 40 days without food. So if you just schedule it properly, you'll be fine. But maybe you don't want to starve. Maybe you want to do something else. So you just put this fridge right in your house, in your kitchen, which means putting cache right inside in your microservice, so no network penalty. And it means that requests from the same user should end up and be processed on the same instance to save network round trips. And then it's not even about network round trip, right? Again, from my earlier slide, you need to go somewhere. Let's say you're hitting the database. If we're talking about Cassandra doesn't have good caching mechanism. So you're most probably going to hit disk. And let's say you're on spinning disk. So now it's 1 month of wait time. Nasty. If you put something in front of it, like Redis or memcached, it makes stuff easier because you'll just need to go to memory because it will not fit in your L1 cache. So you'll still need to do some processing. So wait time is actually increasing. And then do you have time to wait? Maybe you do. Right? Maybe you don't. The catch is, so if we do it, we will need the state that we keep in memory. We also want persistence for it. Because again, soft state used for optimization, it's not meant to be a source of truth. It's not like, I'm not talking about in memory kind of database situation. So every change for the state should be replicated somewhere on this database, for example. And then when you need to pull it in memory, you just pull it from the database. You need also to be able to identify the state with some version number, right? Which means, so to make sure you don't have like weird race condition situation when something changed it on the back end for some reason, and then you just use a stale session from memory. It could be very quick network call to some cache, right, which has this identifier and version in it. And it doesn't have to be sequential. You can do a synchronous check. What you can do, and it's also really easy to implement and possible, in our use case, let's say search comes, what you can do, you just start processing search request. In parallel, you just do a quick check of the version. And then if you see that something changed, you just cancel this thing and then do what has to be done, load it from the database, for example, or do reindexing, whatever you need to do. and continue. Possible to do it in multiple threads. Totally doable. And then again, we'll just need to use this safety guard. So the system will look like this. Actually, you have this database. In our case, it's Cassandra. And the application layer, which has like cache of accounts, Lucene, and then versions in memory so we can compare it. And you might wonder, all right, so if we do something like that, right, how do we know when we do a call, how do we know that we end up on the right server? So servers will need to be able somehow to route users in between, right? There should be some awareness. It's like, I don't have this user, please go to another instance, right? Something should be done. So routing, how do we do it? So there are a couple options. I just listed some of them. First one is like big lookup table. Lookup table could be account ID, for example, or some identifier, server 5, possible. There could be some kind of gossiping algorithm. Databases use it a lot. Cassandra, Couchbase, good example. The idea is all the servers, they are aware of all other servers, because you don't need a lot of memory to store this information. All the servers constantly exchange some gossiping information. They talking to each other and saying, hey, I just saw another server, looks like the server is alive. And then servers can say, and then this server holds all these accounts. You don't need to actually, because the number of, if you just keep exchanging number of things that cached, it can get huge. So you don't need to do it. You can do consistent hashing, kind of the thing where you can say, all right, this server has this subset of accounts. Everyone knows how consistent hashing works? No? Yes? OK. The way it works, you just normalize, literally. You just get your account ID, let's say it's 5. You do CRC32, for example, on it. And then you go to integer. It's a very simple algorithm. Just don't try. Maybe it's not best. It gives you some weird number at the end. And then you do mod on number of servers. It's very simple algorithm for consistent hashing. Cassandra uses murmur 3. It's used CRC before. Doesn't really matter what it is. Route and master, another concept, could be something somewhere that knows somehow magically where to route. It could be round trip to get this information, but still possible. Big question, how to maintain this stuff, right? What if you need to change capacity and you have stuff in memory? Or what if you need to redeploy? If you use in memory state, right, your database at the end can get a hit. And this example, which you can do, again, multiple options. For example, you can use snapshotting, right, if you want to. You can just dump some snapshot every hour on disk, put it on S3s, and magically just start it. You can even go crazier. You can dump the snapshot, put it on S3, spin up an instance, use Packer to burn an AMI, and then use it if you need to scale up. Possible. You can do it with Docker. You can also stream the data, start new instance, stream the data, like 1 billion options, actually. You can do a shadow. We do use it for testing. We call it shadow testing. When you spin up new server and use like shadow traffic to warm it up, multiple things can be done. But we followed, for this one, we followed keep it simple. And then, because definitely we on Amazon, so we used ELB stickiness concept. I don't know how many of you used it. So the idea of ELB stickiness, it uses cookies, like random generated cookies. And then looks like it was created for websites, actually, for browsers, web browsers. And then the way it works, you send the request. ELB looks at it. If special cookie is present, it routes it to a specific server. If it doesn't, then it routes it to a random server. On the way back, it remembers, creates this cookie, remembers some way inside the mapping, gives it back to the browser, and expects the browser to send it back. We needed to do it on server side. And then we had to emulate similar behavior. So we just decided to store those cookies. We're just storing it in our cache. some very simple mapping between account ID and then this AWS sticky cookie ID. And then before the request comes through, we just pull it and then attach it to the request and then send it through the load balancer. And then it's a network round trip as well, yes. But it's actually a fast one because cache is actually really small. Data is really, really small. So the way it works, right, with boxes. Everyone loves boxes. No one loves code anymore. So there's a smart client calls our server. We do a check. If user has a sticky, we just attach it to the request, route it through the load balancer. If it doesn't, then we send request through the ELB. On the way back, attach it, and on the way back, we extract it from the response, store it, and return. Done. So the whole system looked like that. By the way, there's a social network box in a corner, so there will be another talk from our Tokyo team on Thursday, I believe. The talk will be how they moved this piece from MySQL to Dynamo. Will be pretty interesting, recommend to attend. All right, so we have the social network that can send notifications that something changed. For someone friended someone, for example. It goes to an indexer, and the indexer writes it to a Solar Cloud. So this one just only for new users and privacy setting updates. And then it also does this indexing in the background, writes it to Cassandra, and when we need to search, we do split, hit Solar Cloud, hit personalized search microservice, and actually personalized search microservice uses Cassandra for stuff that is not in memory. And load balancer sits right in front of it. Right? That's a high-level idea. So how did it do? Solar was fine. We had like a couple 100 million documents in it. We had our own issues with it, but it was like okay, actually. Some people might say that it wasn't, but like, to me, it was okay. Personalized part was not so fine. What was the problem? So the problem was with this idea, every single change in the friendship required a lot of re-indexing. Just think about it. Let's say there's one person with huge graph on one side, another person with huge graph, and then the horrible thing happens. They just friend each other. So now we have all these multiple indices we need to touch and update. And then same goes for privacy setting, when I don't want to be searchable anymore. Now we need to tell every single index that we store that we need to update it. And you might wonder, like, is it a big problem? It was. We use Cassandra. Cassandra uses SS tables. So the way SS tables concept works, Cassandra doesn't accept updates, right? Every single change is a write, is an addition that goes at some point to disk. So here's an example. Let's say I just friended Dustin. My index got written to disk. It sits there. It's actually consumed space. Then later, Dustin did something, and then my index got touched again. New version will be written again. It will end up in a different file on disk, and so goes on. At some point, Cassandra does a thing called compaction. It goes through all those files. It removes duplicates, and then it generates new file at the end, big one. So it's like removes duplicates. So it means that storage is not released right away, right? It could be that you have a lot of stale data sitting just on disk. And what we saw with this example, storage, like our data size was growing much, much faster than we thought, right? We started with a couple servers. In no time, it grew actually to like tens of servers. And at some point, our management said, that's insane. Let's do something about it. And when we thought about it, our problem was a rapid expansion. Does anyone know how some physicists call rapid expansions? Explosions, right? So we had to just do something about it, and we decided to go back to the drawing board and think how we can make stuff better. So what can we do to avoid such rapid explosion of data? So new beast to tame, and we got this insight from running the system. It's mostly a search session. It means that users don't search frequently. But when it's not a Google, right? When you do it every single day, and definitely not Stack Overflow, right? Yeah, right. So it's more when I need to find someone on the platform, you go inside it, you find someone, and you usually don't do it frequently, but when you want to do it, you probably spend some time typing letters, because you type in letter by letter, going through some names. And then that was an insight. And we thought, oh, what if we do something interesting? What if we use ephemeral indices, right? Indices that we never store inside the database, just a memory index. Those indexes can live in memory just for the duration of search session. And after a user is gone, index can be safely discarded because users might get back in a month, in a year, in 5 days, who knows, but probably not in the next 5 minutes or 25 seconds. And code-wise, it could be exactly the same code. We just needed to move it around from indexer to the application. Now we ended up with similar boxes, but different lines. Right, again, same social network, update, goes to indexer, we just write to Solar Cloud. And then on a read pass, when we hit our search microservice, we can get this friends and friends of friends information, do a really fast indexing, and return the response. In this example, we also, because we cannot use version anymore, there's no storage, right? Cassandra is gone in this example. We also need to know when some friendship information changes so we can avoid having stale indices. And you might wonder, is it fixed yet? Right? We kind of went even further, right? We removed storage so we don't have a problem with storage growing really big and then taking over the world. Not really. It's not fixed yet. The problem is now, because indexing in a read pass, it should be very, very, very fast. When you type first letter, you don't want to wait seconds until we do indexing and respond. And what we noticed looking at our telemetry, that boxes was spending a lot of time in pulling all this data. Right, pulling it in memory, pulling all those bytes and bits. So we just talked about soft state. Can it be improved somehow? It definitely can. We can do some simple math. Let's say we have a couple of 100 million users, hundreds of million users, but number of active users is much less. And then let's say our searchable metadata is just 200 bytes. How much memory will we need to cache all the active users, all the metadata about active users? Not much, actually. If we have 100 million users we want to cache multiplied by 200 bytes, we're talking about 18 gigabytes of RAM. It's not much. So, oops, well, OK. So we can organize everything in memory like this. You probably already figured out by looking at the slides that we use in Java. And then you also probably know that Java garbage collection can kill any good idea. Yeah. So we decided to go with, for caching, with off-heap solution. For this one, we used EHCache. Works pretty well. So Java heap can be small enough, maybe 8 gigs, maybe 5 gigs. For this one, I think we run with 8 gigabytes. Then we allocate some memory for off-heap, and then we can split it into pieces. One piece can be information about accounts. It can be, let's say, 20 gigabytes. We just calculated that we need just 18 gigs. And another 20 gigs can be allocated for Lucene indices. Also, we have SSDs today. And then with Stateless Design, we usually don't use them. Why would you? Maybe to write logs, but then you probably want to move logs to your eventing system fast enough. So you will not probably use all 100 gigs of SSD space. In this example, we can also utilize some SSD space if we need to spill over. It still could be faster than going over the network if we have to. Will it work? Let's look. We have these days, we have 256 gigabytes of RAM on R3 X large, and also has a huge SSD disk. So it looks like from memory perspective, we're good. We have these boxes today. There's one beefy, some monster 2 terabytes of RAM. I don't know. I think you can cache whole world in this box. If you get 3 of them, you'd like set. So I think 10 years ago, that was big data, right? 2 terabytes of memory. Now it's just there. Who knows what's going to be tomorrow? 20 terabyte, I don't know. It's also growing really fast. So it sounds, it can work, but Dustin will actually answer this last question.
The answer is no, guys. Sorry, it doesn't work. We failed hard. No, it actually did work. So just some stats. Everyone loves stats. People like graphs. So here's a graph. Basically, this is showing the amount of accounts cached. So if you look on the right index, we have around 79 million accounts that are cached. And then if you look at the green line, that's our cache hit ratio, and it's in the 97%, which is really good. So we're really utilizing our off-heap cache very well. And if you look here, it's pretty steady. It's not growing. It's pretty, it's performing really, really well with caching all the accounts in PSN. In terms of network, this is the very valuable resource, is that network out is actually really reasonable. It's very small. You think about it, it's about a meg per minute, not much. And network in, same thing, not a lot. If you can imagine in this stateless design where we have to retrieve a lot of this user information and indices, it's quite a bit. And with this design, we have very little network in and out. If you look at the indexing stats, the accounts indexed per second, we have about 700K accounts, users indexed per second, which is quite amazing how many accounts we're doing per second. And the cache hit ratio there is about 50%, not the greatest, but still, as opposed to always hitting a database or anything like that, it's actually quite good. So just some learnings, just like comparing our original stateless design with our soft state design. If you have 122 bytes per user, 730,000 accounts per second with, let's say, 20 servers. So we only have 20 servers that are managing the entire search. With the 0.5 index cache hit ratio, we have stateless design, we have about 509, half a gig per minute versus 14 megs per minute. So it's an order of magnitude larger to do stateless in our case. So when we were hitting network bottlenecks, you can imagine that the amount of servers you would need to accommodate that network traffic could increase the amount of servers you would need. So you can go stateless, but then you would have, let's say, 1,000 servers, and our boss wouldn't really like that very much. So some of the learnings that we have is that you can do wonders when you're desperate. So you have a budget. They say, okay, you have to design this really cool, rich search feature. You have, 20 servers. You have to be able to do it. We don't want to spend so much money on this feature, because you all know that features always bring in all the money, right? So it's something that we really focused on and really found different ways to do it. So stateless works, but it can result in many servers. I think I've heard of systems that have thousands of servers. It blows my mind that even exist. But if you do things like soft state, you can actually reduce the amount you need. You actually utilize all the resources of your box. And you can't beat RAM. Does anybody have anything better than RAM? I want to know. So it's quite good. So that's basically it. You can find us here. So if you're looking for a job, we do a lot of cool stuff, a lot of hands-on. You get to build systems. You get to really not work on the button that Alex mentioned, but you can actually work on cool systems and features. And you can find us this way. Don't try to find us through the Amazon app. You guys know how it is. So that's it. So thank you very much for coming. I appreciate your attendance. And